balance redox equations in acidic solution, and then balance redox equations in basic solutions. Okay, now we balanced, remember, at the beginning of last semester, we balanced by trial and error, but these guys are a little bit more complex. It's a little bit more tedious. So we have a procedure. This is a redox reaction. Okay. Now we have to first identify the oxidation and reduction processes, and then balance the transfer of electrons. Additionally, you will need to account for H and O in both acidic and basic conditions. Okay, that's the first step. Balance the transfer of electrons, then account for H and O. It's a little bit different for basic conditions, so that's why they have separated the two out. So I like this box that lays out the steps for you. Okay, I'm going to write this again. Close this door. Plus Cl2, SO4 2 minus, plus Cl minus AQ. Now, it says add coefficients to balance all the elements but hydrogen and oxygen. Okay, so there's no hydrogen here yet, but there's oxygen. So let's balance the sulfur and the chlorine. Now assign oxidation numbers to all the elements. Sulfur, we have to find out what that is. Oxygen is -2. What is Cl in Cl2?
0.
0. Now sulfur and sulfate, we have to find out what that is. Let me call that Y. Oxygen, all of these cases is -2, just a charge on the ion, okay? And each chloride, we are looking at each ion or element or atom. So each chloride is -1. Can we solve for the oxidation number of sulfur in S2O3, 2 minus? Can you go ahead and do it? Let's practice. And also the sulfur and sulfate. Jessica, what do you have for the sulfur in the thiosulfate? The first one is thiosulfate.
Is it 6?
Is it +6? You get something other than 6? Each oxygen is -2. This is 2x. Each oxygen is -2. And the charge on the whole ion is -2. Okay, learn the method. 2x minus 6 is -2. 2x is -6 minus 2. That is -8. So what is?
Dr. Mary, it should be
It should be +6. Yeah, +6. So this is +4.
So it's going to be a 2.
2, yeah. Okay, so I know why she said 6, because she looked at that and thought it was 6. So that's a common mistake. +2. No, the method. Can you try it for the sulfate?
That one is +6.
Oh, this one is +6, okay.
Yeah.
So this is X, there's only one sulfur, okay, everybody listening? Plus, there's 4 oxygens and each oxygen is -2, and then the total charge is -2. So X minus 8 is -2, and X is +8 minus 2, this is +6. Okay. So you have to go through this process. You balance the atoms, and then you find the oxidation number for each one. If you know how to do these two, then you should be able to do them all.
Dr. Mary,
Yeah,
sorry to bother, but actually on the thiosulfate, like how was the total 6? How did we know that it was 6, the total?
are you
For
seeing
S-
this calculation here?
Yes, ma'am.
So the sulfur, we don't know what it is, so we are setting it as X.
Mhm.
And then there are 4 oxygen atoms right here.
Mhm.
And each oxygen has a charge of -2, the oxide.
Mhm.
And then the sum of these charges, because it's not a neutral ion, the sum of the charges equal the charge on the ion.
Okay, yes, ma'am. Got it.
Okay, this net charge is the same as that.
Yes, ma'am. Got it. Thank you.
So if it's a neutral compound, then it'll be 0. But since this is an ion, it's -2. And then you solve the equation.
Yes, ma'am.
Same here. This though, there are 2 sulfur atoms. So you put this as 2x plus 3, and each oxygen is -2, and the charge on the ion is -2. And then you solve for it.
Got it. Yes, ma'am. I got it. I'm clear now. Thank you.
Okay, all right. So this X is +2. And this Y, I called it Y because it's different from this one. This is +6. Okay, so now the next step is identify those that are undergoing changes. So oxygen is not undergoing any change. Okay, no change. So the sulfur goes from +2 to sulfur +6. I'm just going to barely, like crudely write it like that. And then the Cl goes from 0 to Cl -1. So which one is undergoing oxidation and which one is undergoing reduction?
Sulfur is undergoing oxidation and the other one reduction.
Okay, so Cl to -1, gain of electrons is reduction. This one, it's becoming more positive, right? Increase in oxidation number. You have to remember definitions. Loss of electrons is reduction. How do we do this? Write the oxidation half reaction and the reduction half reaction. Okay, so the thiosulfate to the sulfate, okay, write it like that, like how we did for conjugate base and conjugate acid, remember? So this is oxidation. And the other one is reduction. So oxidation half S2O3 2-, giving 2 sulfate 2-. Okay, crudely we write it. Now, Cl2 gives 2Cl minus. Now we have to balance these. How will you balance the charges? This is 2-, right? The charge here. Look at the net charges. There's 2 of these, so that's -4. And this is going from 0 to -2. Okay, now let's look on the next page. I think I'm missing a step here. Let's look at it. Now let's look at the oxidation half. And go to the next page. Balance oxygen by adding water. Okay, so let's look at the oxidation half reaction. I have S2O3, 2 minus, giving 2 sulfate. Now, I'm not able to balance the oxygen. See, I have 3 here and I have 8 there. All right. So I'm not able to balance the oxygen atoms with what I have. So add water to the side with fewer oxygen atoms. Okay. With fewer oxygen atoms. So this has 3 and this has 8. So I'm going to add water here. Then of course, because I'm adding water, then I have to balance the oxygen and then I have to balance the hydrogen. So oxygen, I have 4, and then I have 4 here. Next, add hydrogen, H plus, to the opposite side to balance the H's from water. Okay, looks like a tedious process, but once you get the hang of it. Okay, so I'm going to add H plus. So this is going to be an acidic solution. That's why the H plus. Okay, so this is 2. So looks like everything is, no, what happened here? I forgot about the 8. So this is 3 oxygens, and here I have 8 oxygens. So how will you balance this? How many water molecules do you need?
5.
Yeah, that's right. Okay. So this would be 10H plus. Okay, so once you have the oxidation half and the reduction half, then you add water to the side with fewer oxygen atoms. And then because you're adding H's, you need H's on the other side. Okay. Now is when we look at charges. I'm going to rewrite this. That's all I'm doing. Now balance the charges, because we need to know how many electrons are transferred. So this is neutral. Net charge is 0. The net charge on this ion is -2. The net charge on this is 4 minus. Net charge on this is 10 plus. You see how I'm deriving the charges? This is neutral. The charge here is -2. There's only 1 ion. 2 minus, but there are 2 ions, so 4 minus. 10 hydrogen, so it is 10 plus. Net charge on the reactant side, -2. What's the net charge on this side? It's +6. Okay. So now I have 2 minus here and I have 6 plus there. How will I make it equal by adding electrons? Can you tell me? I'm going to rewrite this. How many electrons should I add and where to balance this? I don't have to make each side 0, but I have to make it equal. So if I retain this as -2, how many electrons must I add here?
Are we making it all the way to -2?
Mm-hmm.
So 8.
8 electrons?
Yeah. Since they're a negative charge, would end up.
So this, you're adding 0 here, -2, and this is -2. So you add 8 electrons to the side. This is still a half reaction, but it's a completely balanced oxidation half reaction.
Why did you add 0 to the left side?
Because I'm not adding any more electrons, but here I'm adding -8 electrons to make these two equal.
So you want to make the right side equal the left side.
Yes. But the only way I can make it equal is by adding electrons to one side or the other.
Dr. Mary,
Mhm.
how do we know which one of both are we gonna set equal the equation to?
That's why I said you can only add electrons. So it's that side that requires electrons. That's the only side you can add electrons to.
Okay.
Anybody else? You have to make these two charges equal. The net charges on both sides must be equal. Remember, you need to have the same number of electrons leaving the anode and the same number of electrons reaching the cathode. And so here's where the charge balance happens. And the only way you can balance it is by adding electrons to one side or the other. You don't have any protons to add. The only things you have are electrons. You can only add electrons to one side or the other to make the charges equal.
So for the final answer, do we have to write plus E like at the end?
Yeah, we have not finished it yet. Now look at the reduction half reaction. That's simpler because it doesn't have any oxygen. So go back and look at the reduction half reaction. Okay. Cl2 giving 2 Cl minus. And it's balanced except for the charge. So balance the charge. So here this is 0 net charge. This is -2. How will you balance the charges? This is 0, that's -2. What will you do? This is a simple example.
We add -2 to the left side.
-2, or what will you add? 2 electrons, right? So that
2 electrons.
yes, very good. So this is a net charge of -2, and this is also a net charge -2. And it also proves a point. What is that? Reduction is gain of electrons is reduction. Oxidation, you see, electrons are lost. So loss of electrons is oxidation. Now, to write the overall, what must you do?
You have to balance the electrons on both sides.
Yes, very good. So that's 8 electrons. So you have to multiply this whole thing by 4. So I'm going to rewrite this here. 4 electrons plus 4 Cl2 giving 8 Cl. I'm sorry, this is 8 electrons. Giving 8 Cl minus. So now, to get the overall balanced equation, I'm going to write everything down but the electrons, because I've canceled those. Seems like a long process, but as long as you go stepwise, you'd make fewer mistakes. This is the balanced equation. Okay, so I have to see how the electrons are balanced, how the how they are made equal, and then overall balanced equation. We're going to do another one, so we review, and this is also an acidic. Okay, so first step, I'm going to say the first step is to assign oxidation numbers. Okay, do this first, and then we can move on. And this is 2. Okay, and then 3 will be writing half reactions. Okay. So assign oxidation numbers. Now some are more obvious. This is +2, this is +3, right? The charges. What's the charge on the oxygen? What's the charge on the oxide? It's always
-2.
-2. Okay. Here also it's -2. Now I'm going to give you a minute. I want you to balance. I'm not balance. I want you to find the oxidation number. We've done this in Gen Chem 1, just that we have forgotten. Find the oxidation number for chromium and find the oxidation number for tin. Look at what we did. Take your time. Well, not a whole lot of time. Tell me what you get. Did you all print out that table with the potentials? Or you should have your appendix A5 or A2, I don't remember now. Let me know what you get for chromium. You can write it in the chat.
So I got 6+ for chromium and then 4+ for SN.
SN, what is SN?
Strontium.
What did you get? Tom, what did you get? Tom's not here.
He just wrote something in the chat.
Just ask if you can hear him.
Oh, can you hear me? No, can't hear you, Tom. Do you have yourself muted? Brandon's here. -6 for Brandon. Yeah, I think so. Thought you were giving me the oxidation number. -6 is good.
Oh, what? Okay, so for chromium is 6+, and then for the other one is 4+.
Yeah, she's giving
For strontium, Kevin.
strontium or tin.
10.
Tin, yes. Okay, so it's +6. I was printing the oxidation table, the reduction table. Okay. So let's do it quickly so everybody can review. 2x plus 7 times -2 is -2. Do we remember the method? Okay, then 2x minus 14 is -2. 2x is 14 minus 2, and so that's 12. 2x then is 12, x is +6. Okay, that's right. And remember, oxygen, for all the problems that we will do in this chapter, it's always -2. And hydrogen is +1, okay? So the standard charges apply. SnO2, so this is Y, I call it Y, +2 times, there are 2 oxygen atoms, so this is 0 though. There's no charge on the compound or the formula for the compound. Y is +4. Okay. Okay. Got it? Know the procedure. Your post lab for lab will have some problems like this because you need to review this. So now go back. Chromium is +6, and this is +4. So chromium I'm going to put all the chromiums together, right? Like the acid and conjugate base. And then the next set, 2+ giving SNO2. Now, this is +6, and this is +3. So is this oxidation or reduction? And this is +2 going to +4. So which is oxidation, which is reduction?
The first one is reduction, the second one is oxidation.
That's right. So this is decrease in oxidation number. Increase in oxidation number. All right. Now we'd have to balance each one individually. Oxidation half. And we'll need water for both.
Dr. Mary, I found a way of remembering how to know which is oxidation and reduction, just to help these people struggling with the GERLEO.
Yeah, didn't I say
So
that?
if you write down the word, so if you write down the word oil rig, OILRIG, you can remember both of them, because then it spells out oxidation is loss and reduction is gain. So if you just remember that, then you can know the two.
Yeah, remember. And then also what I use is gain of electrons is reduction, loss of electrons is oxidation. So Leo says GER. You can use both to remind yourselves. Okay, yes. Thanks, Francis. So here you have extra oxygen. This is the oxidation half. So you add water on this side. And there are 2 oxygens, so 2 water molecules. And then I add H pluses on the other side, so 4 H pluses. Okay. Now, let's do the electron balance as well. So look at the charges. I have +2. From water is 0. From SnO2, it's 0. From hydrogen, it's 4+. So how will you balance the charges? What must you add to balance the charges?
Add
2
2 electrons to the right side.
Yes. Electrons to the right side. How many electrons? 2 electrons, right?
2.
So here the net charge is +2. The net charge is +2. So remember, when balancing the charges, you don't have to have 0 on each side. You just need to have the same number on each side. Okay. So I'm going to write the balanced oxidation half. So I have SN2 plus 2 water. After I finish this, I'll go back and continue with the voltaic cells. I've added 2 electrons here. Okay, again, like Francis said, oxidation is loss of electrons, or loss of electrons is oxidation. Now, can you give me a balanced reduction half reaction? What do you have? That's the one with the CR2, 07. Now, let's balance the chromium. That's 2. Now, balance the oxygen. There's 7 here, there's none here, so I'm going to put 7 molecules of water. And because I have 7 molecules of water, I need 14 H pluses on this side. Now balance the charges, okay? So you've finished mass balance. Next, charge balance. So I have 14 positive. Okay. There's 2 here, 2 negative, 6 positive, and 0. 12 positive and 6 positive. So how will I balance the electrons?
Dr. Mary, in this case, wouldn't we try to get +6 on both sides?
Oh, what did I say? Yeah, how will you get +6? What should you do to get +6 is my question.
Add 6 electrons to the left side.
Okay, so you cannot get the balance until you add the electrons. Okay, so I'm going to put 6 electrons here. And now I have a balanced reduction half reaction. I'm going back to that page. Got this? This is 14H plus Cr2O7 2 minus plus 6 electrons, giving 2 Cr3 plus 7 water. Well, I see each one is balanced, but to balance the overall, what should you do? You need to get rid of electrons. So you should multiply this whole thing by 3. So what do you have? This is 3 SN2 plus 6 water, giving 3 SNO2 plus 12H plus, right? Plus 6 electrons. Now we will be able to also consolidate all the water and everything. Okay. So let's write, I like to write it down and then take care of it. 3 SN2 plus 6 water. I'm adding up all the reactants. Canceling the electrons. On the product side, I have 3 SNO2 plus 12H plus 2 Cr3 plus 7 water. Now I have 6 water molecules here, 7 here, so I'm going to subtract 6 water molecules minus 12H plus. This is also minus 12H plus. I'm squeezing everything in. I need my long dry erase board. All I'm doing is I'm canceling the excess molecules of water. So ultimately I'll have 3 SN2 plus 2H plus Cr2O7 2 minus 3 SNO2 plus 2 Cr3 plus 1 water molecule. You may be able to cancel the water molecules and the H plus more easily and with less mess, but this is the final answer to that question. Any questions?
Do we have to include the state symbols?
Say that again?
Do we have to include the state symbols, the aqueous, liquid, or solid?
Yes, theoretically, yes, you're right. But if you got caught up in the process and do not do it for this particular equation or these equations, I'll be okay with it, okay? Or at least at the end, go back and add those. That's
All
a
right, great.
proper way for a chemist or a scientist to show the answer, okay? Okay, now I'm going to go and I'm going to do an example again on Tuesday after I ask you to do some homework problems, and then I'll also tackle the basic solution. If you do the acidic solution, then you do the same thing, and at the end you make some changes, but other than that, it isn't very different, okay? And I'll try to post all these slides too over the weekend if I can. Okay, now I'd like you to try this for Tuesday. I know I had some homework for today as well. Okay, so try it in acidic solution, and then I'll show you a shortcut at very end to switch to basic. Now let's go back. Let's see where we left off here. We're talking about the standard reduction potentials and how they measure the cell potentials. Okay. Now let me get the table that I printed off. And remember, we skipped section 19.3. We're not doing the redox titrations. Grab that chart. Okay. So this is like the Ka table. These values will be given to you either in the form of a table or the values will be given in the problem as well. Okay, so for your lab, you have to use these tables. So how do they come up? Like for example, I'm going to use this. Zinc, you remember the half cell has this potential. How do they come up with this value? And look at it, these are all written as reduction reactions. Why are they reduction reactions? Because they are gaining electrons. So these are all reduction reactions. That's how they've written it, okay? So now, if they want to find the reduction potential for zinc, then they'll connect the zinc anode compartment with the standard hydrogen electrode. Remember, this is used as a reference electrode. That means they've set this value to be 0. All right, so this I said is like a blank solution when you did the visible, like the absorbance readings. So it's similar to that. So they will connect this. This is She, which is standard hydrogen electrode. And since they have hydrogen gas in hydrogen in an acidic solution, for electrical connectivity, they're using this inert metal strip. Okay. So then whatever the voltmeter reads, that is assumed to be the reduction potential for zinc, because this is set equal to 0. So the voltage here will read as plus 0.76 volts. And so they say the anode compartment's voltage is plus 0.76. And we'll learn why the reduction potential is reversed, right? That sign changes, we'll talk about that a little bit later. But this is how they come up with the table. So next they remove this, and they've done it with lead. And they've done it with gases as well, not just the metals, the non-metals as well, okay? And here's the table that's in your textbook. I put it all together. And these values were not correctly entered in the textbook, so I had to fix it by looking at other sources. So look at these values. These are all reduction potentials. And these are all values for half reactions. The other half reaction being the hydrogen electrode. So whether these reactions take place spontaneously or not, they are written as reduction half. Gain of electrons is reduction, gain of electrons. I'm stressing this again because you need to know how to read the table. So you have all the electrons on the reactant side. Now, I did tell you delta G has to be negative for a reaction to be spontaneous. All right. Now, for a reaction, electrochemical reaction to be spontaneous, delta G equals negative constant values multiplied by the voltage. So for delta G to be negative, then this voltage must be positive. Okay. So E0 that you calculate, E0 that you use for spontaneous reactions must be positive. So look at all these reactions. These all have positive values. See that? So these reactions, half reactions, are spontaneous. Okay, these reduction reactions are spontaneous. Are you with me? Look at the next set. Below that of hydrogen, you see that? This is 0. All the metals, though, what do metals generally like to do? Metals like to become cations and lose electrons. Okay? They like to do this. This is spontaneous. Now, if you tell the cations, pick up some electrons and become metals, this is non-spontaneous. So oxidation is spontaneous, reduction is non-spontaneous. And you see from these values, these are reduction potentials. They're pushing these guys to pick up electrons and they are refusing negative, 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 more negative, 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 and lithium and sodium, and they are all group 1. They revolt the most. Okay. They want to look like the nearest noble gas. Now they're asking them to pick up electrons and become less stable, and they are not for it. Okay, general tendencies that you have to know. All right, what do we do with this? Standard, okay, again, we've looked at standard before. We know gases are at 1 atm. Temperature, usually room temperature, 25 degrees centigrade. And if you have solutions, these are 1 molar, and any solids and liquids are pure substances. Okay, any solids and liquids. Okay, standard reduction potentials. Now this is what you'll need to do your data sheet calculations. Okay. E0 of a cell. Now remember, a cell is made up of the anode compartment and the cathode compartment. Just like the universe is made of the system and the surroundings, cell is anode and cathode. So E0 cell, E0, okay, this is for the whole cell, is E0 cathode. We're not going to add these two up here. Got it? Cathode, at the cathode, reduction takes place normally, right? At the anode, it's oxidation. Therefore, in order to take that into account, you have the negative sign. And this is the standard reduction potential. It'll become clear when we start doing problems, okay? Any reactant, this is important to know. In table 19.2, that's the one that I just showed you, will react spontaneously with any product. Okay, any reactant will react spontaneously with any product with a lower potential in the table. I'll give you an example. Fe3 plus an electron gives Fe2 plus. Can you find the E0 value for this from your table? Fe3 plus to Fe2 plus. Is it given in your table? Yes.
.77.
Yes. So this is positive, okay? Now, below that, I'm going to pick nickel 2 plus an electron plus 2 electrons. Okay, so it's going to become nickel solid. What's E0 for this?
Negative 0.26.
Negative 0.26 volts.
I'm sorry, 225. 0.25, I think.
Yeah, one place they have 26, one place they have 25. Okay, 25. Doesn't matter. Whatever you have, write it down. So they are saying this reactant will spontaneously react with this product. And right here, I'm going to show you why. Okay, so this is possible. Now, let's calculate E0 cell. Is E0 cathode minus E0 anode. Now, the one that is positive or the one with the higher reduction potential will be the cathode. Because it has higher E0 value. And we'll be looking at more examples like this. So E0 cell is E0 cathode. This is the cathode. And this is my anode. E0 cathode is 0.77 volt minus 0.25 volt. The sum becomes positive. You see that? E0 cell is positive. So when I make this guy the cathode and this the anode, then I'm going to have a spontaneous reaction. So my cell will look like this. You remember? So I'm going to have nickel and nickel 2 plus. And this is going to be, I'm going to have both iron 3 plus and iron 2 plus. And what will I use? I'll use platinum. Okay. So this is my anode. This is my cathode. And the voltage shown here will be 77 plus 102 volts. And this engine will run. You're beginning to understand? We'll be doing more examples. Let's do the next example. So you have to remember this rule, okay? Reactant in table 2 will react spontaneously with product or products with a lower potential. So remember this diagonal rule. But this guy must be higher up than this guy. And there's another rule. I'll come back to it after we look at a couple more examples. Okay. So we have this cell. And the question is, you have these two half cells. Okay. In the lab, that's what you would have done. And I would say, you know, construct a cell. And when I say construct a cell, you should have an anode and a cathode. And only if it is, if you have the right anode and the right cathode, will you have electricity flow through. You'll have electrical charges flow through. Otherwise, it'll not show you anything and you'll have to flip. Okay, that's what you would have done in lab. So now I have these two half cells. I want to make a cell that has a positive voltage. Only then this is spontaneous. Okay, so how do I pick the right anode and how do I pick the correct cathode? So let's look at the reduction potentials. Okay, they say find the standard reduction potentials in table standard. Okay, I have copper 2 plus 2 electrons giving copper, and E0 from the table is plus 0.34 volts. Okay. And then the second one, zinc, I'm just writing it down from the table. I'm not doing anything else here. This though is negative. Okay. Copper is okay. Copper 2 plus is okay gaining 2 electrons, but zinc is not okay gaining 2 electrons. Okay, now from the rule we just learned, okay, I've arranged this in, this is higher, this is lower. Are you all following me? What's the rule?
Yes,
To
ma'am.
make, okay, thank you. To make it spontaneous, this reactant can react with this product. Okay, what that means is this likes to remain this way and be the cathode. And if he should react with zinc, then zinc should flip. See that? So this guy is the anode. And it's all trial and error. You know, if you get E0 cell as negative, then flip the 2. So in my cell, I'm going to have zinc. You don't have to draw this every time, but I'm doing it so you understand. And this is what we did the other day, right? Copper 2 plus and copper. Remember we talked about the salt bridge. All those are required. Okay. Now I'm going to use this formula. E0 cell is E0 cathode minus E0 anode. Okay. So E0 cathode, if I assume this to be the cathode, this is the anode. Hope you remember how to draw the cell notation. I'm going to ask for that after we finish this here. This is 0.34 volts minus 0.76 volt. Now, does that give you a positive number? 7, 6, is it positive 0.110? So if you connected the anode correctly and the cathode correctly, then your voltmeter would read 0.110 volt.
Dr. Mary, it's 1.10.
Yeah, that's right, right? I'm forgetting my math here. One point one zero. Now, if you had flipped it, and you might try that too, you will get a negative value, and then you'll be like, okay, I have to switch it. Okay, so it's an easy way to correct yourself. I have an example here. Let me try this. First, I would like the cell potential. I'm going to do one example. SN4 plus slash SN2 plus. How will you write that as a half reaction? SN4 plus giving SN2 plus. Balance it. And then CR3 plus giving CR2 plus. How will you balance these? Plus 2 electrons. And this is plus an electron. Okay. First step. Write the and it's important that you write reduction. Can you find the values from your tables? Or table, if you have it all together. CR3 plus. Plus an electron is negative 0.41 volt. And then tin is positive 0.15 volt. Okay, so it's in the order. See this? This is higher, it so happened. This is lower. So the diagonal rule applies, reactant, product. Okay. The reactant can successfully react with CR2 plus and make the reaction spontaneous. Okay, so make sure that you have the higher number up. It's so important if you're going to follow this rule. And then the cathode is the one with the higher E0 reduction. And this becomes your anode. Okay, can you calculate E0 cell and tell me if you get a positive value? And then write the cell notation. What's the answer?
Zero 0.56.
So you did 0.15 volt, E0 cathode minus E0 anode, minus of minus 0.41. You got plus 0.56.
Yes.
Yeah. So it is spontaneous. Okay, you have to acknowledge that. Can you write the cell notation? No, both compartments. Any questions about this? I'm just following the process. This is the rule. Always put the higher one on top. And if you do, then this is your cathode and this is your anode. If you flip it, it's okay. You'll get a negative E0 cell, then flip it back. Cell notation. Now, there's no metal here. You see that? These are all aqueous solutions. So remember, you have to put the metal platinum solid for electrical connectivity. And when there is a phase change, single line, and then write the reactant 4+. This is an aqueous solution. So you say 1 molar, right, for standard, comma, SN2+, 1 molar aqueous solution. Now we are moving to the, no, wait a minute. What was the mistake that I made? How do you write the cell notation? How do you write the cell?
Oh, you forgot the CR?
Yeah. So you write the anode first, right? And then the cathode. So I started off incorrectly. Okay, I'm going to rewrite it here. Anode is the one with the lower potential, so that is CR2+, CR, I'm sorry, CR3+, CR2+, and then I have SN4+ / SN2+. Okay. And both of them need platinum. Because there's no solid here. So start with platinum. And then I have CR. See that? CR2+ is going to give CR3+ in the anode. So it is CR2+, 1 molar, CR3+, 1 molar, salt bridge. And then you have the platinum again. Start with the reactants. Product. Okay, so this is the cell notation.
Dr. Mary, I have a question.
Just a second. So how do you write it? This is the cathode, right? For the cell notation, you have to show the anode first and then the cathode. And then the cathode You see how you've written it? SN4 plus gives SN2 plus. And then SN4 plus reacts with Cr2 plus. So this is written first and then Cr3 plus. Okay. Because this guy reacts with this. So this is your reactant in the anode, and this is your product in the anode. Yes, what's your question, Kevin?
Never mind. You just
I just answered it, right?
yeah.
I knew that. I'll try not to give anything with all solutions, but if you do have something like this in the on sapling, that's how you would do it. Okay. Now I'm going to let you do this because I want to get to the next part. This will be homework as well. I'm going to the next section. The remaining examples, I'll do it on Tuesday. I want to get to this last part so you have everything that you need for lab and sapling and homework. Okay. So now we are going to relate, and already have given out the answer. That's the relationship between free energy and the cell potential, okay, under standard conditions. So this is a constant. This is also a constant. So you need a negative delta G. Okay. So this is under non-standard conditions. N is the number of moles of electrons. You remember the electrons that you balance? You balance the electrons. If you have 3 in one and 2 in the other, you multiply by a common factor, not a common factor, but you multiply by appropriate factors to make the number of electrons equal. So it's that number, okay? Faraday, this is a constant that'll be given to you, like the value R. This is so many coulombs per mole of electron. So that's why you multiply this by moles of electrons. And this is called as the Faraday constant. Okay, that's coulombs, by the way, electric charge. Delta is delta G0. The only changes E0. Okay, under standard conditions, and you remember 1 molar for aqueous solutions, 25 degrees centigrade, 1 atm for gases, and solids and liquids are pure substances. Okay. Now we calculated the Daniell cell is specifically referred to this one. Zinc I'm going to write the equations. Then you had copper. I'm going to put copper up on top. Okay. The voltaic cell is what they're talking about. Now, Do you remember what you got as E0 cell for this problem? Okay, E0, reduction. Let me show it quickly. This is minus 0.76 volt. And this is, copper is positive, plus 3,4. Okay. And this is higher. So this is your cathode. Anode. Okay. Cathode is plus 0.34 minus of minus 0.76 volts plus 1.104. Okay, so that's the first part. Calculate the E0 cell. Now, to write the overall reaction, oxidation half. Okay, oxidation half happens at the anode. So zinc goes into solution as zinc 2 plus and 2 electrons. Reduction half. Copper 2 plus 2 electrons gives copper solid. And how many moles of electrons do we have? 2 moles. So the overall reaction is zinc solid plus copper 2 plus AQ, giving zinc 2 plus copper solid. Okay. Now I did this to show you that the value of N is 2. So what is delta G0 minus NFE0 minus 2 moles of electrons multiplied by 96,485 coulombs per mole electrons multiplied by the 1.10 volt. What do you get?
Negative 212.0.
12 or scientific?
2.12 times 10 to the 3.
2.12 times 10 power 3 or?
I got 10 power 5.
Yeah, I think so.
Yeah, that's what I meant to say.
Oh, really? Okay. So Coulomb volt, what should that equal? What unit does delta G have normally? Free energy? Okay, Jessica. She has to go. What is free energy? What are the units for free energy?
Joule.
Joule. So Coulomb times volt is nothing but joules. Okay. Now you can convert this to kilojoules and be 10 power 2 kilojoules if asked. Okay. So this is not a difficult calculation. Now, if we can calculate delta G, then what else can we calculate? E0, we got delta G0. What else can we calculate? Are you reviewing chapter 18?
Delta H.
Yeah, you can do that too. Equilibrium constant, right?
Yes.
So process for this, I'm going to do a problem with K and then we'll finish with that. So here you should calculate E0 cell like you have been doing. And then you need to be for sure how many electrons are transferred. And you have to balance the number of electrons. Here it's already balanced, so you didn't have to do anything. And then after that, you just use those moles of electrons, this constant and this, and the answer will directly be in joules. And if asked, you'll have to convert that to kilojoules. Okay. Next, we are going to see the relationship between cell potential and the equilibrium constant, and of course, that will be through delta G. Okay. So delta G0, remember, minus RT ln K, and I'll also supply the equations that you will be given. And delta G0 is also negative NFE0, right? So what can we do? We can equate those two. So negative NFE0 is minus RT 1K. The negatives can cancel. And divide both sides by negative NF. Okay. So easily you can calculate K. Okay. Got this? Now we're going to use the E0. Go down to the next slide. E0 for the cell 1.10 volt, okay, for the cell that we saw. They're asking you to find K. So rearrange the equation. You have to go backwards now. Multiply both sides by NF. Divide both sides by RT. Here, ln K. Okay. Can you find ln K first? N is 2 moles. F is 96,485 coulomb per mole. E0 is 1 plus 1.10 volt. R. Which R must you use?
The one that is like 8.3 something.
Yes, very good. Because we're still talking about energy, right?
Yeah.
Joule per Kelvin per mole. So here we have an unnecessary mole, and we'll worry about it later or ignore it for the time being. Can you calculate L and K first, please? One last calculation for the day.
$85.67.
85.67. Okay. Now that's L and K, right? Did you all get that? Next, can you find K?
$1.6 times 10 to the 37.
Okay. It depends on how many sig figs you have here. It's very sensitive. Any questions? We tied everything together. So as long as you know how to identify the cathode and the anode correctly, and then of course the balancing in that acidic solution, those are the ones that could be a little tricky, but practice is needed. Did you get the answer? Did you get something else? Anybody else get a different answer? If you rounded this to, if you rounded that to 85.7, then you'll get a slightly different answer here. Now one last slide. So delta G and delta, E0, this is the relationship. This was the first one we saw. I like this chart. And then we included this, and then we have that. Okay. So with that, we finish. Any questions?